Okay, so now we're going to get into the more complex calculation of a weak-strong titration. Before we actually do the calculation, it's useful to analyze the important conceptual ideas that we want to use. Step number one is to analyze any major species that are present. After you place the substance in water, but before a reaction takes place. And for this, you need to go back to the idea that with strong acid and strong bases, they completely dissociate. Whereas for weak acid and weak bases, there's only very slight dissociation. So the idea being that if I have HA and it's a strong acid, then what I would see is not HA, but I would see H plus and A minus in my solution. Whereas if I have HB, let's say, and that's a weak acid, then what I would see in solution is the HB molecule itself, not the ions. That's the first part of the analysis. The second part is to ask the question if there's a significant reaction that will happen among the species that are present in that solution, a reaction that has a large K. Because if the reaction doesn't have a large K, that means that there's no reaction, and so whatever we have before is still going to be what we have at equilibrium. It's just the same species. But if there's a reaction, then some of those species might disappear because they're going to convert into a different molecule, a product. If you're able to identify a significant reaction, then what you have to do is figure out what happened after the reaction's equilibrium. What are the major species that are now present at equilibrium? And to help you in calculating the pH, you want to categorize your solution at equilibrium as one of the 5 solutions I'm listing right here, which is a strong acid, a strong base, a weak acid, a weak base, or a buffer. The reason we want to do this is because once we know if it's one of those 5, we can go ahead and use the appropriate method to calculate pH. So if it's a strong acid, all we need to do is find the H plus directly from the strong acid. If it's a strong base, we're going to directly find the OH minus and use 14 minus POH to find the pH. If it's a weak acid, we're going to need to look at Ka and set up an ice table. If we have a weak base, we're going to need to find Kb and an ice table. And if we have a buffer, we're going to have to use the Henderson-Hasselbalch equation. So there's complexity that happens here that we didn't have to deal with in the strong-strong titration. In strong-strong titration, all we have is these 2 cases right here and water. Right? Whereas now we have introduced 3 additional possibilities. All right, so we're going to go through this analysis of a weak-strong titration just the same way as we did strong-strong titration by looking at now a weak acid, which is acetic acid, which has that Ka value, titrated with a strong base, an AOH, and the concentration and volume values are given there. And the same way as we were analyzing the strong-strong titration, what we want to do here is completely fill out this table with pH values for the different volumes of NaOH that's been added to the solution. So this is talking about total NaOH volume. We want to be able to calculate the pH at all of the spots that are blank right now. Okay. Now you can see that some of those spots already have value. That's because the calculations of those would be similar to the ones that I would show you. So I'm expecting you to be able to calculate those and match them to the ones that are already listed. So let's start with the first one, which is 0 milliliters of NaOH added. If you think about the solution at the beginning, before you add anything, well, all you have in there is your acetic acid. If you go back to this analysis idea, you can say, well, at the beginning, all I have is a weak acid. My major species is going to be the weak acid itself, acetic acid. And then the question is there any reaction that might happen with acetic acid on its own? Nothing is added to it. So the acetic acid is just going to act like any weak acid would. It will dissociate slightly. So then at equilibrium, all you have is still the weak acid. So there's no reaction. Therefore, your analysis stopped pretty much at step number 1. And then in step number 4, you identify the solution as a weak acid. So you need to use Ka and the ice table to find your pH. And that's exactly what I did here with 0 milliliter of NaOH added. All I did was to set up my weak acid equilibrium. This is the concentration initially, and then we're going to lose a little bit of stuff due to the slight dissociation. Then we're going to have these as our equilibrium concentration. Our solution of this is just using the Ka value, which was given in the question, and then finding X, which is the proton concentration, to be 1.34 times 10 to the minus 3. Notice, of course, that I'm using the small k approximation for that denominator. So that would give me a pH of 2.87. That's my first number here. It should be 2.87. Now, what about when I add 5 milliliter of NaOH. Slightly different now because if you start adding, now there's going to be a couple of species present. First is still the weak acid, but then I also have NaOH, which I know is a strong base, so it's just going to break apart into Na plus and OH minus. So what I have in my solution is my weak acid, Na plus, and OH minus. And so just the same way as I was analyzing earlier, I'm going to ask myself, is there a significant reaction that takes place with species? Well, it turns out there is. The significant reaction that happens here is the reaction between OH minus and the weak acid. The sodium doesn't really react, it's just a spectator ion. So you can write this significant reaction as follows: HC2H3O2 plus OH minus, and the product will be conjugate base plus water. Now the key here is to recognize that this is a significant reaction. The criterion is to find a reaction with a large K. This reaction has a large K because if you look carefully, it's actually the reverse of a weak base reaction with water, right? If it's a reverse reaction, that means the K is going to be the reciprocal of the K of the reaction of weak base with water. Now, what's the K of a reaction of weak base with water? It's Kb. So now the K of this reaction is 1 over Kb. We know that Kb has a small value, it's much less than 1, so that this reaction must then have a K that is much larger than 1. That's the reason why we call it a significant reaction. Okay. Now that we know it has a large K, the way we are going to solve this problem is just go ahead and work out an ice table. The reaction itself is written here. Acid plus OH minus goes to conjugate base plus water. Since there's a reaction with large K, we know that there's going to be two reactants. One of the reactants is less than the other one, so this is a limiting reactant situation. So we're going to have to calculate the number of moles. But of course, when we later on need to use K to help us solve the problem, we still have to bring it back to concentration. It's just that during the ice table calculation, we convert them back to moles. So to calculate number of moles of the acetic acid, I just multiply the molarity and the volume, giving me 2.5 millimoles. For hydroxide, I get 0.1 molar times the 5 milliliter I've added, so that's half a millimole. I put those numbers as my initial values. I don't have any of the conjugate base. The water column you can see is blank because water doesn't factor into my K expression. And then because this is a reaction that goes to completion, the limiting reactant is going to be completely consumed. The limiting reactant is hydroxide, so all the hydroxide is gone. And then the conjugate base now is getting half a millimole. At the end, this is what I have. I have 2 millimole of acetic acid and I have half a millimole of conjugate base. Now remember what I said in that last analysis. What major species exists at equilibrium after the reaction? Well, we just determined it's the weak acid and its conjugate base. What solution do I have? I have a buffer, right? That's a solution where both the weak acid and its conjugate base exists in appreciable quantities. So therefore, to solve for pH, I'm going to use my Henderson-Hasselbalch equation, which is pH equals pKa plus the log of A minus over HA. My A minus is acetate, my HA is acetic acid. And if I plug in the numbers I was given, I have my Ka. My concentration is just half a millimole divided by 30 milliliters, my total volume, and then 2 millimoles divided by 30 milliliter. I end up getting 4.14 as my pH right now. So in fact, right after the beginning of the titration, I've already entered this buffer region of the titration. So 4.14 is the pH for that portion, okay? I'm gonna leave it up to you to go ahead and calculate that 10 milliliter addition. It's going to be exactly the same as the one we just did for 5. Again, now the total volume of NaOH added is 10 milliliter. So calculate that out. But I do want to spend a little time talking about the 12.5. The 12.5 is a unique spot here. It's unique because when you add 12.5 milliliter of NaOH, you have exactly half the number of moles of acetic acid. So in other words, if I set up my ice table with 12.5 milliliter of NaOH, I'm going to have 1.25 millimole of NaOH, which of course means 1.25 millimoles of OH minus. The acetic acid is 2.5 millimoles. So that means that this is exactly half of that number. And that means we've reached half the equivalence point, right? Because the equivalence point is when all the acids have been neutralized. So this point in a weak strong titration is what we refer to as the half point or half equivalence point, or sometimes you'll see it written just as half EP. This is a important point during titration, because when you solve for the pH, you'll find that because you have taken out exactly half of your acid, if you look at this same reaction here with the ice table, but replace this quantity with now 1.25, you're going to have negative 1.25, negative 1.25, and positive 1.25. So you have 1.25 and then 1.25 right here. The thing I want to highlight here is that these two numbers are the same. So if I calculate their concentration in my Henderson-Hasselbalch equation, they would just cancel away, and you have the log of 1, and the log of 1, of course, is 0. So your pH is equal to just your pKa value. And that's what I wrote down here. It's a very important idea because at this point, your solution in the flask is the most optimal buffer possible. It's the strongest buffer it can possibly be. We had discussed how to make effective buffers, so I would ask you to look back at that lecture. The thing we had said at that time is that when pH is equal to pKa, that's when a buffer is the best at what it does, which is resist pH changes. So this is the point in the titration of a weak strong profile where we have our most optimal buffer. Okay, so this number I'm going to fill in for you. It's 4.74. When we go from really pretty much from here to here, these are regions where my solution is a buffer. On the top here, I have a weak acid when nothing has been added. So I would encourage you to again calculate this one, and this one as well, because they're all done the same exact way. But then now we want to get to 25. And again, 25 is another unique point during my titration. Why is that? Because at that point, you've added exactly the same number of moles of OH minus as the amount of acetic acid that you have. So therefore, all of the acetic acid and the OH minus are gone, leaving you at equilibrium with only the conjugate base. So going back to our analysis step, after the reaction reaches equilibrium, what major species exist? All I have now is A minus in my solution. And what is A minus? It's one of these five. It's a weak base because the conjugate base of a weak acid is a weak base. So therefore, if I have a weak base, I need Kb. I need my ice table to find pH. And that's what I'm going to show you right now. Then I have to write a weak base reaction with water, which forms the conjugate acid and OH minus. And to do this calculation, I'm going to use my ice table and Kb. And again, since I'm using Kb, I'm going to need to use my concentration values again. So what I did right here at the top is just to calculate the concentration of the acetate, which is 2.5 millimole. That's the acetate that I have, divided by the total volume. The total volume here is 25 of the acetic acid plus 25 of the NaOH. So as a result, it adds up to 50, and the concentration is 0.05 molar. Doing the calculation here, I have 0.05 minus x, and x at equilibrium. Now I'm going to need to use Kb. Kb is Kw over Ka. So we can calculate that way. That gives us this number as Kb. And then we set that equal to x squared over 0.05 minus x. And so the Kb value will allow us to calculate x, which actually stands for OH minus concentration in this case. So therefore, to get the pH, we have to subtract 14 minus POH, and that gives us a pH value of 8.72. That's the number I'm going to fill out in my table as the pH at equivalence point. So this is my EP, my equivalence point. Now, immediately something should jump out at you. Earlier, when we were doing strong titration, the equivalence point is at pH equals 7. And that's because the quantity of base and acid exactly neutralize each other, and all we're producing is water. In a weak strong titration, you don't produce just water, but you produce water plus be a weak base or a weak acid. In our particular titration here, we're producing weak base and water. In strong, we just produce water. So it's the weak base that's going to determine the pH, and that's why we get a basic pH here at our equivalence point. So very, very important to keep that in mind, okay? I underlined it here that in a weak strong titration, the equivalence point is not pH equals 7, okay? pH is not at 7. It might be higher than 7 or lower than 7, but it's not 7. All right.